Hi everyone. So today we'll do chapter 12. I have a worksheet that I made up just to hit the highlights of chapter 12, and then we'll go over some problems at the end. So in the next video we'll go over some examples. This is my basic plan of attack for the rest of the semester, basically. So today we'll do chapter 12. Next week we'll do chapter 13. The week after we're going to do the rest of the material for the class. That's my hope. I hope I can fit it all in 1 week. So for now, what we're going to talk about is population proportions. When we talk about proportions in this context, what we really mean is percentages. So we're talking about proportions of a population that has a certain characteristic or that shares a certain belief. These don't necessarily have to be samples of people, but that's really the context where many of these ideas are most prevalent. So what we're going to do is we're going to talk about the population proportion and inferences that we can make on the population proportion based on samples. So here, this is again inferential statistics, where we take a sample, we figure out what does that tell us about the underlying population, and there's some different tests that we can use to go through and figure out what are the different characteristics that the population has based on the sample. So we're going to use the character P to denote the population proportion. So remember that this is a parameter because it refers specifically to the population. Given a sample of size n, P hat is going to be our sample proportion, so that's the proportion of the sample that has that certain characteristic. To compute P hat, we take the number of members of our sample that have the certain characteristic, and then we divide by the size of our sample space, n. P hat is how we're going to say this quantity, so this is P hat. And it turns out that there's a lot of nice things that happen for sampling proportions. The first is that if you were to take the mean of all of the sample proportions, what you would end up with would be the population proportion. And likewise, the standard deviation of the set of all the sample proportions has this formula. It's the square root of p times 1 minus p all divided by n. What this means is that we're going to be able to use everything that we know, and if we know the population proportion ahead of time, we're going to be able to determine exactly the mean and the standard deviation of our distribution, and it turns out that this is going to be normally distributed if n is large. Okay, so since everything is normally distributed, at least when n is large, we're going to be able to use the normal distribution, which means we have z-tests and z-scores and the standard normal distribution. So no t-tests, no student t-tests with degrees of freedom, none of that. None of that's going to be relevant for this chapter. So what we're going to do first is we're going to talk about single population proportions. The idea is that you have a single population. You want to know what's the proportion, what's the percentage of the people in that population that, say, support a certain candidate or like some piece of legislation or support a certain sports team, whatever. Okay, so you want to know what's the proportion of people in that range that has whatever certain quality you want. So the first thing that we're going to be able to do is, if we have a sample, we're going to be able to give a confidence interval of where that population proportion is. So again, what that means is that we're going to have a certain confidence level, say 95% confidence level, where that 95% is kind of the standard confidence level for anything. So if we have a 95% confidence interval for a population proportion, that means that there's a 95% chance that the population proportion is in that interval. Okay, so again, that's the idea with the confidence interval. The confidence interval is going to have the same, sorry, I have a creaky chair today. The confidence interval is going to have the same layout, the same format as all the confidence intervals that we've talked about so far. You take the mean plus or minus your critical values times the standard deviation. Okay, that's how we're going to find the confidence interval. The part after the plus or minus is again called the margin of error. So this piece here, z sub alpha over 2 times the square root of p hat times 1 minus p hat all divided by n. That's called the margin of error for the estimate of the population proportion. Most often you'll hear different polls or different samples stated with the margin of error, so that you know roughly the margin of error that we have with whatever confidence. So typically what people want is for a 95% confidence interval to have at most a 3% margin of error. So if alpha is 0.05, we want to figure out how large does n have to be to ensure that this margin of error is small enough. Notice that when n is really big, since it's in the denominator here, when n gets big, this whole thing gets small. So if we choose n large enough, we can make sure that the margin of error is small enough, right? And that makes sense, right? We will have smaller error as our sample size increases, because if we have, say, 1,000 people that we're sampling versus 20,000 people, the sample with 20,000, a sample size of 20,000 is going to give us a much better idea of the population than a sample of just, say, 1,000, right? So as n increases, the margin of error decreases. Okay, and so here's our formula for the confidence interval. One of the other issues that comes up is oftentimes we want to know how many people do we have to sample so that we can be certain that a margin of error is small enough. And this is a little bit tricky because what we know is that we can find the confidence interval based on if we have a significance level alpha and if we know the sample proportion. The problem is that ahead of time you don't know the sample proportion, and so oftentimes what you have to do is guess. And one of the guesses that you can make, and this is a guess that's based on calculus, it turns out, so I want to look at this p times 1 minus p, or I'm just going to call this x times 1 minus x. It turns out that that x times 1 minus x quantity is going to be largest when x is 1/2. Okay, so if x is 1/2, meaning that this is 1/2 times 1 minus 1/2, so 1/4. So the largest value that this is going to take is going to be 1/4, and you get that value when x is 1/2. Okay, this is a straightforward 4th week of Calc 1 exercise that you should be able to do. Maximize this function, x times 1 minus x. Really, that just means find the derivative, and so on. So I'll leave that to you to fill in the details if you've taken a calculus course before. If not, no big deal. We just need to know that p times 1 minus p is going to be largest when p hat is 1/2. So if we know nothing at all, the most conservative estimate that we can come up with is if we have p hat being 1/2. In other words, if this quantity is 1/4. And so if we choose that value, we know that if we have n that's at least that large, we'll have a margin of error e that's at most whatever size we want, right, for whatever value of e we plug in there. That's if we have no idea what the underlying sample proportion is going to be. If we know that the sample proportion is probably going to lie within a certain range, then what we can do is we can pick the value in that range closest to 1/2. So, for example, if I know that p hat is going to be between, say, 0.3 and 0.8, then our guess, this g, by the way, stands for guess, but our guess, we would choose the value in that range closest to 0.5. Since 0.5 is in that range, 0.5 is our guess. If on the other hand we had, if we know that our proportion p hat is going to be, say, between 0.1 and 0.3, then we could use as a guess for our proportion, we would use the point in this range closest to 0.5. So that would be 0.3. Okay, so that's how we get this guess p hat sub g. That's our guess for the sample population proportion. All right, so that's confidence intervals and sufficient sample size to keep our margin of error small. The next idea is hypothesis testing. So what we're going to do is we're going to want to test whether or not our population proportion is equal to some value, and our alternative hypothesis can be two-tailed, left-tailed, or right-tailed, again, just depending on whatever our situation is. And it turns out that once we have our significance level alpha, we can compute our test statistic, and the test statistic is this quantity, right? So we take p hat minus p naught, all over the square root of p naught times 1 minus p naught over n, all of that being underneath the square root. That's our test statistic. Once we have our test statistic, you can use the critical value approach or the p-value approach. The choice is yours. Whatever you prefer there is fine. Okay, so that's if we have one population proportion. I should just point out that for one population proportion, what we're trying to figure out is you have a certain population, and you want to know what's the proportion in that population that have some certain characteristic, right? What's the proportion of, say, college students who have taken a psychology course, right? That's a certain proportion that you can take, and then you can take a sample of college students, ask them how many have taken this psychology course, and you can kind of infer about the population that way. So you just have a single population, you want to know what's the proportion, that's it. That's one population proportion. In contrast, we can also talk about two population proportions, and the idea here is that you have two different groups of people, and then you want to know, are their proportions going to be the same for whatever characteristic or different? So let's say you have a set of college students who are biology majors and a set of college students who are chemistry majors. And what you want to know is the proportion of biology majors that take a psychology class the same as the proportion of chemistry majors that take a psychology class? You want to know, are those two proportions equal? So we're going to call P1 the proportion of the first population. P2 is the proportion of the second population. Our null hypothesis is always going to be that the two proportions are equal. The two population proportions are equal. The alternative hypothesis can then be that they're not equal. One's less than the other. One's greater than the other. Okay, so that's our two-tailed and then one-tailed alternative hypotheses. We again choose a significance level alpha. We compute our test statistic. Our test statistic, by the way, involves this funny quantity p hat sub p. This is what's called the pooled population proportion. And so what this is if, again, you think about, say, the first population being biology students, the second population being chemistry students, this pooled proportion is what you get when what you do is you're going to group all of those students all together. So you look at the whole pool of biology and chemistry students, and from that pool, you want to know how many of them have taken a psychology class, right? So that's called the pooled population proportion. That's the quantity p hat sub p. And again, you use this value. It's slightly different because, again, we have two population proportions. So this is very much like what we did last chapter when you had to look at, say, the pooled standard deviation, right? You had these complicated formulas. This is the formula that we just need to contend with here. It's a more or less straightforward formula. You just have to remember what each term is. So again, P1 hat is the sample proportion for the first population. P2 hat's the sample proportion for the second population. P sub p hat is the pooled population proportion, as we just described. And then N1 and N2 are the sample sizes for the first and second population. Once you have the test statistic, you can just basically revert this to a Chapter 10 problem. You can do the critical value approach or the p-value approach, whichever you prefer. If you do the p-value approach, you do need to use some sort of p-value calculator like R or whatever your favorite p-value calculator is that you have. Okay, so I think R is the easiest here if you want to compute the actual p-value. But you can do either the critical value or the p-value approach. So again, the critical value is once you have your alpha, once you have your significance level alpha, you can compute your critical values. And then if your test statistic lies in the rejection range, then you reject the null hypothesis. If it does not lie in the rejection range, you do not reject the null hypothesis. Remember that the critical values are part of the rejection range, as always. If you have a p-value approach, then really you just compute the p-value of your test statistic. Remember that the p-value is the probability of your data being at least as extreme as the data that you have, right? So this is the probability of a random data set being at least as extreme as the data that you have. And so if p is smaller than alpha, you reject the null hypothesis. If it's larger than alpha, you do not reject the null hypothesis. And if it's equal to alpha, again, that's part of the rejection region, so you will again reject the null hypothesis. One more thing to talk about here is confidence intervals for two population proportions. Here we have a formula for how to find a confidence interval given a confidence level alpha, or given a significance level alpha, so your confidence level is 1 minus alpha. And so it turns out that this is the quantity that you'll use to get a confidence interval for the difference in the two population proportions. So here, this is going to give you some interval that's going to contain the difference in the population proportions. Notice that this does not tell you what either proportion actually is equal to. All it does is it tells you, are the population proportions likely to be this close, or are they likely to be not this close? So in other words, this gives you a range, right? This gives you a range for P1 hat minus P2 hat, right? It tells you that this is going to be in some certain range. Or to say it another way, this tells you that your first population, P1, is within however many units of P2. Okay, so if we add P2 hat to both sides, this kind of gives you a range that P1 hat's going to be within this interval, right, from P2. So again, this doesn't tell you exactly what the value is, P1 hat. It just tells you how close is it to P2 hat. That's really what it tells you, is the difference there. All right, next we'll do some examples.